Here we see a circuit diagram and a state diagram taken from the textbook, representing a binary counter, counting from 0 up to and including 1, 1. On the left, the state diagram includes two flip-flops of type T, and on the right, you see the state diagram. Both of these are represented as a Moore model. Let's take a look at some Verilog HDL code which implements this Moore machine. The first set of code we're going to look at implements the state diagram. The code we have in front of us has a few things which you may not have seen before. The first is a parameter statement. A parameter statement, which I'll highlight here, is a way to define constants. In our state diagram we have 4 states. The constants you see here, S0, S1, S2, and S3, represent those 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. They're implemented here as constants. The second thing that may be new to you is the always block. The always block can be thought of as running continuously. It's triggered when one of two things or both happen. When the clock input has a positive edge transition, or the reset pin has a negative edge transition. When those things happen, the always block code is executed. Looking at the if-else logic inside the always block, it's all about transitioning from one state to the next. For example, from S0 to S1 and so on. This particular always block implements the state diagram that we saw previously. The last line of this module assigns a value to the output based on whether or not we are currently in state S3. When we arrive in state S3, the output will go high or become 1. Now the second example we're going to take a look at, which implements this binary counter, implements the structural diagram we saw previously. But there's a couple things here we need to be aware of. Here's our structural model. You'll notice it's a little bit smaller, not necessarily less complex. But if you look at what's going on here, this uses flip-flops along with the input equations to model the circuit. We have 3 assigned statements here in the middle, which in effect implement the gates of our structural model, as well as the output. And we have 2 flip-flops down here which are instantiated. And they use this type toggle flip-flop 3. This is a T flip-flop. So we're using 2 T flip-flops as indicated in the earlier structural model. But where does that code come from? This is code that was talked about earlier in the chapter, and here's what that code looks like. With a T flip-flop, the purpose of this Verilog HDL module is to implement the characteristic equation. Again, it uses an always block with the same triggers, the same transitions which trigger the always block. And using that characteristic equation, it sets Q, the output, to be one of 2 things, either 0 or Q XORed with the input T. So this module implements the flip-flop. This module uses that code as part of the circuit that it's modeling. This is very similar to in C++ when you have functions and you use functions inside of other functions, sort of like building blocks. So we have 2 models of this particular circuit. One, as you see before you, the structural model based off the circuit diagram, and the first based off the state transition diagram. The test bench that we use is actually going to test both. Here's the test bench, or test fixture as they call it in Exalinks. As you can see, it's not real long, but it does test each of these 2 models. Now, these 2 lines here are where we instantiate one variable for each of the models. Now the first, called M1, is an instance of the state transition diagram. The second, called M2, is an instance of our model of the circuit diagram. Now looking at the code which follows, we have a lot of similar code, although it's slightly different. We have two initial blocks, one here and one here, both of which execute concurrently or in parallel. Now they do slightly different things. With this first one, it's all about changing the reset and the clock pins. And you'll notice that we have a repeat loop down here at the bottom which repeats 16 times, changing or complementing the clock unit every 5 nanoseconds. The second block here is all about changing the X input. You'll notice here that every 10 nanoseconds in this repeat loop, the X input is complemented. By having these two blocks which execute concurrently, we can model both of these particular implementations. Now when I run the simulation, the output provided by Exalinks shows us the waveforms for a bunch of different variables of interest. The clock, the reset pin, the X input, Y output for each of the particular implementations, and A and B, which is the output of each of the flip-flops. And looking at the waveforms, we notice two things. One is they match the example provided in figure 5.24 of the text, which is expected. But they also show us the transitions, and it's something we can use to verify that the circuits are working as expected. One thing we can definitely take a look at is the two outputs. Are the two implementations doing the same thing? Are they producing the same outputs based on their own implementations? And we see that they both go high and go low when expected. In that sense, these two lines of output here are identical, and that's what we wanted. We can also get some finer level of detail by looking at the other outputs and making sure that everything there is going well.